Hi, I'm Mark Flieger with CortechSplanations, and this is a demonstration of the event pipeline in EMSE for one subject, for starters, and we'll also do a within subject permutation test to compare two conditions. So our data here that we'll be using, we're starting from a recording which is also on another video for our participant DV, Dimitri Boreatis. And in that live session recording, we had a session that created 7 replications of an N170 face perception task that was came directly out of Neurobehavioral Systems presentation, one of their standard ERP programs. Okay, so we used that. We made 7 replications of it, and in the live session recording we made live averages, but now we're offline. We're going to go back to these raw BDF files, and we're going to treat all of these together as if they're one file, and we're going to make averages of face stimuli and car stimuli, and we'll do a permutation test to compare the difference between those. Okay, let's see how that works. So let me go back here. I actually let me go back one step. There is a zip file that contains the contents of what I'm starting with, so you can obtain that file from us, and then you can do this yourself. Okay, in addition to the raw data, which is under the DV folder, there's a proto folder. This is prototype data, a small sample of data we collected in order to put some filters in the pipeline, and now we want to apply those same filters here. So let's see how that works. Alright, let's start with a blank slate. Let's start with a new workspace, and let me just save it right away so that we'll navigate to the folder we want. Okay, we're already there. Let me call it DV N170, same name as the folder. I'll save that. Now you can see we just have added a WKS file to that folder. Okay, let's in the first project let's rename it Proto. Let's right click on there, add a time series data. Let's go into the Proto folder and let's just add the BDF file there. I'm going to double click on this. This is a small file, and principally we want it now because it has attached to it the filter pipeline that we want to apply. So in particular, it has a probe. This probe, we can look at it. It's for a 128 channel recording. This is a standard set of locations for those 128 channels. And there's a digital reference montage. In this case, we're applying a digital linked mastoid reference. We have a spatial interpolation filter, which during the recording there were 2 channels we didn't quite like, so we're spatially interpolating channel A14 and channel A16. Those are the only 2 channels we're spatially interpolating. We're applying a digital IIR filter from 0.2 to 50 Hertz. And finally, there's an express ocular correction filter. All those filters were applied live to make some live averages, but on the other hand, these filters were not applied to the saved data. But we want to do so here. We want to treat the saved files all together. So, okay, let me unload this one. Let's right-click here, make a new project. Let's make this, let this be our real project that we want to analyze, and we'll call it DV for the participant's name. I'll right-click on the DV project, add time series data. Okay, let's go to the DV session 1 folder and let's click Control Shift. We'll select all 7 replications. And now we have them here in the workspace. The workspace hasn't been saved yet, so let me do that. Okay, next we would like to treat all of these together as if they were one long recording. So for that, let's go to Utilities, Concatenate Files, and we're going to make what's called an EMSE meta file. So let me select on the DV folder to select all 7 replications. Let's give a name for the meta file we want to create. So let's go back to the main folder. Let's call it dv_s01_n170. I'll say save. It's going to save it as type EMSE-MF. That's an EMSE meta file. And let's add it to the DV project. And I'll say OK. OK, so here it is. And if we happen to look in our folder, we'll see that a new file has been created with the extension EMSE_MF. It's very small. It's only 1 kilobyte, and it points to these 7 replications. Okay, now what we'd like to do is, before we load the meta file, we'd actually like to copy the filter pipeline. So I'm right-clicked on the prototype file, copy the filter pipeline. Now I'm going to right-click on the meta file, paste the filter pipeline. Okay. Let's save our workspace, and then let's double-click on the meta file. All right. So here, our meta file should now be starting with the very first replication, repo 1, and it should actually point to all of these files. So let's actually look at the events. I'll go to Edit, Events, Edit Event List, and let me sort on the name and see the seg marker. These. So there's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 seg markers, which the first one marks the beginning of the first file, and these, and then the remaining 7 are at the beginning of each subsequent file. So these, for example, if I select this first one and say go to, okay, we can now see, I'm going to cancel, we can now see we've gone to the first discontinuity in the data. That is between the first replication and the second one, and you can see there's a discontinuity there. So indeed our meta file is concatenating all of these, and we can see that the filter pipeline contains exactly what we had in the prototype. So all of those filters now are being applied to all of these data files via the meta file. Okay, so that's our first step. Now let's let me save the workspace and let's go to the event pipeline. Okay, so I'm going to go to Batch Event Pipeline, and the first step of the event pipeline is to select a sample data file that contains all the events that we're interested in. So in this case, let me just let's see here. The EMSE meta file is showing on top, which has been resorted. Well, let me select the meta file itself, because each replication may not have all the events we're interested in, but the meta file itself has all events across all our replications. So let me select the meta file. Okay, now steps 2 and 3 are only necessary if we're trying to make some complex event logic, but here we don't have any complex event logic, so we can skip directly to step 4, which is to specify bins. Alright, so I'm going to skip to step 4 and edit for step 4. Okay, we're going to make 2 bins, one for face stimuli and the other for car stimuli. And I happen to know, so let's just call our first bin face. And I happen to know that the events in the experiment that had event codes from 1 to 40 were faces. So let me select all of those. Control-Shift-Select. Now we've selected all those, and I'm going to say Add Bin. So what we now have a bin called Face that corresponds to the first 40 event codes. Okay, let's make another one called Car. Okay, so these were stimuli of cars of various kinds, and they were the first car started at 41 and it went to 80. So let's go to 80 here. Control-Shift-Select, and we'll add that bin. Okay, so now we have a bin called Face and a bin called Car, and they are both sharing the same epoch specification, which is generally what we want. But let's go in and actually edit that specification. Okay, so this is defaulting to a 200 millisecond baseline and 800 milliseconds following the baseline. Let's keep that. Now, since our event pipeline, or since our filter pipeline, I should say, has a digital IIR in it, let's add a custom interval with a little bit of padding in it. So let's add 100 milliseconds at both ends. Okay, this is gives the filter the opportunity to warm up at both ends. Gives us an extra 100 milliseconds. So that'll be our custom interval, even though our interval of interest that we'll end up with is 200 milliseconds baseline to 800 milliseconds afterwards. Okay, so we do want to do baseline correction. That is simply polynomial order 0. And we want to use the pre-stim based on the interval of interest. So our baseline correction will be for 200 milliseconds. Okay, let's apply some rejection criteria. So EMSE is defaulting to plus or minus 100 microvolts. These are in volts units. So let's say we want to be a little more strict. Let's say we want to go from minus 75 microvolts to plus 75 microvolts. So I'm going to put minus 75 e to the minus 6. Since EMSE's units are volts, the e to the minus 6 puts us to microvolts. And I'll put here for the high end 75 e to the minus 6. Okay. And so those are our rejection criteria, and all of that is going to apply to both faces and car bins. Okay, so we're done here. I'm going to say okay. Next, let's select our time series, and here we really now only need this one, the meta file. If we had multiple participants, we could be the event pipeline could be applied to other participants as well, but here we're just focusing on within subject analysis for DV. Okay, so that's all we need is the meta file, which actually contains all this information already. Skip over processing options. Let's go to output. Okay, we're going to in this case we're going to make time domain averages. In another demo, we'll do some time frequency analysis on the same data. I recommend that you start with time domain when you're doing this for the first time, just to make sure it all processes smoothly. And then once you're getting good time domain averages, then you can move to time frequency, and you can do it in parallel. Okay, we only have one participant, so there's no grand average here. So I'll just say okay. And really we're done. So let's say now execute. So what the event pipeline is doing now, it's going through all the events in the meta file, finding all the ones in the face bin, and we're making an average for that bin called face, and it's automatically giving this average the name face underscore DV. Now we're doing the same thing for the cars. So we're going through the car bin and making an average for that with the applicant criteria that we made, including the rejection criteria of plus or minus 75 microvolts. And all the filters are being applied. Okay, so now that it's finished, we have in our workspace we have two averages. So let me unload this meta file. Let's before we look at it, let's see the face. Let's look at some properties. We see that here we see that out of a total of 69 candidates, 10 were rejected. And for the cars, we can see that properties out of 68 candidates, only one was rejected in this case. Okay, so let's load the face. I'm double-clicking there. We can also see this down at the bottom, see the blue accepted 59, rejected 10, total 69. Okay, there we have the face. We're seeing it in chart recorder display. We can let's do the channel array display, and from this we can see we have some apparently some pretty nice looking responses. If we look at it in superimposed display, we can see there's some apparent component here at about 120. milliseconds, and then we have before the 200. This somewhere in here we expect our there's 170 milliseconds. So somewhere in here we expect to see our face response. Okay, actually, let's suppose we want to map that. So let's right-click on DV. Let's use one of our resources. Let's add a scalp wireframe. In the resources here, let's add the scalp. Let's load that scalp. And now at this cursor point, let's just map that. And sensor scalp. Let's say we want to have contour over the map and apply it. Okay. So here we can see there's a dominant response here on the right. Let's save that, and let's select a little more there and apply that. Let's go back to that view. Yeah, so we have some lateralization here. Still some response on the left as well, but lateralized on the right. Okay. Let's go back to channel array display, and let's right click on the car bin and overlay that. Okay, so here we have our car response. Everything seems to be quick view of it. Looks like it kind of overlays pretty nicely, but here at channel B10, if I double click there and zoom in on that, we can see there is indeed a large difference. So the black is the face. There's a large negative response at channel B10, and there's a less negative response at the same latency. Here, this is about 189 milliseconds for the car. All right, so let's move ahead now to the permutation test. So let's save this workspace. Let's say now we want to test the hypothesis that there's a significant difference here, but we want to test it across all channels, not just this one. We want to have multiple comparison corrections for both space and time. But let's restrict our hypothesis to a time range from about, let's round it to about 250 to let's say from 100 to 250. Okay. Let's move to statistics and permutation test. All right, so in this case we want to demonstrate a within subject test. So we have the test will be performed at the level of the single trials. And the comparison type will be unpaired. We want to compare the faces with the cars, but those are not paired in the sense of, let's say, in a sensory gating experiment where you might have, each trial might have an S1 followed by an S2. There would be pairs of stimuli in each trial. We don't have that here. So we're going to be doing an unpaired comparison, not a paired. And let's look in the time domain here. It's possible to do time frequency and frequency domain. We'll do that in another recording. All right, we want to look at the mean, which means we're going to be doing like an ERP, that is averaging. And we've got multiple comparisons to worry about. So we've got space, we've got 128 channels. We have time, our time range of interest. And we need to correct for all of those multiple comparisons. So we'll do a global correction, meaning we're going to do both space and time. And we're going to do a permutation test. So each time we will iterate. If we iterate 100 times, the very smallest p-value we could observe would be 0.01. If we iterate 200 times, the smallest p-value we could obtain with 200 randomizations would be 0.005. Let's do that. Okay, so I'm going to say next. Now, one thing I didn't point out, but underneath the face average and underneath the car average, each has a meta file, which points back to the raw data. And here now we can actually see them. So there's a car meta file, which is pointing to all the single trials that were labeled as cars. And there's a face meta file. It's underneath face. And it's pointing to all the single trials that were labeled face. Okay, so let's select those two, and I'll say next. Now, what we want, we're going to have a condition on the left minus a condition on the right. So let's say we want to do faces minus cars. Okay, notice that our conditions now have been relabeled with the bin name, not the original code. So the original codes were 1 through 40 for faces, 41 through 80 for cars. They've been nicely relabeled by these meta files that were made by the event pipeline. Okay, so let's do face minus car. Event acceptance criteria, let's look here. We don't need to add any new acceptance rules because the meta files that made our averages already rejected trials with plus or minus 75 microvolts. So we don't need to apply any addition rejection criteria here. So I just wanted to show you that. Another advantage of using the meta files that were made by the event pipeline. Okay, let's go next. And here, because now we're doing statistics, let's set an interval of interest for statistical comparison. Let's say we want to go from 100. We could be more or less conservative here. If we're more targeted in our interval of interest for statistical comparison, our test will be more powerful. We might miss significant differences outside the interval that we specify here. But if we have a more specific hypothesis, we can test it with greater power by specifying it here. That means that the correction for multiple comparisons won't need to be as stringent because we're not correcting for as many multiple comparisons. Let's say we want to go from 0.1 to 250. Okay, let's say that's our interval of interest. And our filtering interval, however, okay, so we still need to correct for the baseline correction out here. So even if our interval of interest is in here, we'll still need to do baseline correction out here. So we need a custom interval for filtering that does include a pre-stimulus baseline. And so let's go out to 200 milliseconds. We don't need to pad it because it's already padded for our interval of interest, although, take that back, we want to do baseline correction out there. So let's do pad it another 100 milliseconds like we did. We made these averages. And then at the end, let's pad it, say, out to 400 milliseconds. Okay, so the padding, as you recall, is so that we will allow our filter to warm up. Okay, let's go next. And here we do want to do a baseline correction. But let's use a selected interval. Let's say we really only want a baseline with the 200 millisecond interval. Okay, so let's say finish. Okay, so now what's happening here? First of all, the permutation test is preloading all of the single trials that are face single trials and car single trials from these meta files. So they've already been pre-rejected. We're loading exactly the same single trials that made those averages. Now, at this point, we're reconstructing the averages 200 times. More precisely, 199 times, I should say. The first time is without any scrambling whatsoever. The face minus the car as we see them here. And then 199 times more, where the face trials and the car trials are being randomly mixed together. And so if we imagine that the face, we have two urns, one that has face marbles in it and another urn that has car marbles in it. 199 times we're scrambling those marbles together and we're relabeling them as cars and faces, even though it's purely random. So our null hypothesis is that the labeling of these trials as car and face makes no difference. Okay, we're done. So let me go out to this level here. Let me make a new folder called, let's call it face minus car. And let's also call this face minus car. Okay, we're saving the results of the permutation test. And let's add this to a new project. Let's also call that face minus car. Okay. Okay, so we've made a new project. It's being added to the workspace, and this project has the statistical comparison in it. Let's save the workspace. Let's add to this one, let's add a probe from our resources. We have the Biosemi 128 file. All right, so now we have of the results of the permutation test, we have something called group 1 mean. Okay, so that's whatever was in group 1, which of those were faces. However, it's only in the time interval of interest, which is from 100 to 250 milliseconds. The group 2 mean is the same thing for cars. The delta mean means the delta is the difference, so it's group 1 minus group 2. And then what we're really interested in are these p-values that have been globally corrected for multiple comparisons, and there are 2 of them. So actually, if we go back to our original averages here, the thing that we noticed at channel B10 is that the face was more negative than the car in that time interval. So of these, the first set of p-values, the one that's labeled max, will be p-values where the face would be greater than the car, and the one labeled min will be the p-values where the face is smaller than the car. Now in this case it's more negative, which is less than. So let's double click this one here, the one that says min. Okay, let's take a peek at this in channel array mode. And what we can see here right away is, let's take an arbitrary channel like B13 here. If I double click there, you don't see anything there. That's because all the p-values are 1. After globally correcting for multiple comparisons, there's nothing significant. But if we look at the channel we were originally looking at here, channel B10, and I double click here, notice that the labels are in the lower left hand corner. So this is channel B10 here. If I double click there, now we can see in this time interval of interest, which goes from 100 to 250, that's our interval, we see here in that time range from about 180 to about 198 that the p-values there are as small as can be. So we're getting our most significant results here in this time range that corresponds to this time range we noted in the original averages. Now let's say we just want to map that. So let's do a flat map here. And yeah, we can see that the significant difference between faces and cars is concentrating itself. It's the small values that are significant here. So the large values are 1. The small values are about, as small as they can possibly be, given that we only did 200 permutations. Okay, but we can see there from the map, we can see there's some others which turn out to be, if we go back here, they turn out to be adjacent to so B8, B9, B10, and to some extent B11. If we look at B11, it's giving us a little bit of a hint, although these aren't achieving significance. They are nonetheless a hint that even after multiple corrections, there appears to be some difference between these two. So that's that's giving us some kind of a hint that there may be a difference between those two latencies. All right, now what maybe if we look at this one that says max, it can show us latencies where the face response was greater than the car response, and they seem to be showing up at longer latencies. So for example, here we're seeing it at channel A23 out here at around 215 milliseconds. And if we let's do a map here, see what these are showing up. Yeah, interestingly, the small values are showing here right on the midline. Channel A23, if we go up here, the face, let's see, channel A23, let's zoom in on that. We can see here, indeed, there is a difference here where the face is larger than the car. And according to our permutation test, that turns out to be significant. Okay, so that's our demonstration. So what did we do? We started with some raw data. We concatenated them all together. We applied a filter pipeline that we had previously used during acquisition to all of them. We used the event pipeline to make two bins, the car and the face, and from that we made a couple averages. Underneath each average is a meta file. Okay, I didn't really show that to you before. We used them. So this is the face meta file. It's pointing, this face meta file is pointing to the raw data that contains all the single trial faces that were included in the average. So here they are. And similarly for the cars, there's a meta file under there. And actually we used those meta files in the permutation test. Okay, so let's stop here and we can resume. We can resume at another time to show, for example, time frequency analysis within subject.